A letter of lecture. I am Ochita K. Taro. I use computer automatic voice. The automatic voice reads the manuscript I created. I am honored to speak in front of you. And thank you for taking the time to listen to my lecture. I am an applied mathematician and information processing engineer. Japanese characters are written in blue. Let's get started. Functions created by God. How do you solve the following differential equation with arbitrary differentiable functions a, x, and b, x, as coefficients? I'm sure I will solve it. Because I know the formula of the solution of the above differential equation. I used some hyper-exponential functions to create it. Furthermore, I derived hyper-exponential functions from the differential equation itself above. That is, the hyper-exponential functions are functions defined by me, but they are inherent in the differential equation itself above, so have been created by God. And since the hyper-exponential functions have been created by God, they are expected to be applied to a wide range of fields. The aim of this lecture is to introduce the hyper-exponential functions to you. Theme. I show you the definition of a new special function called hyper-exponential function. Hyper-exponential function is a family of special functions that contain exponential function. I show you the basic characteristics of the hyper-exponential functions and how to generate them. I use hyper-exponential functions to show a new solution of differential equations. Symbol. I use EXPH as a symbol means hyper-exponential function. Its trailing h is the initials of hyper. The form of hyper-exponential functions of n order. Hyper-exponential functions are usually generated as infinite series. Seed of the hyper-exponential function means the first term of the series. If there are more than one seed, you differentiate them by the number. The main feature of the hyper-exponential functions of n order. The n-order derivative of y is the product of f, x, and y. Hyper-exponential functions are classified by the order above. The feature of hyper-exponential functions of second order. Two hyper-exponential functions of second order that are generated using a function f, x, one is the first term 1, and the other is the first term x. These two functions are linearly independent. Graphs of the hyper-exponential functions of second order. The graphs listed above were drawn by Mathematica. Drawing sine and cosine curves showed that the program can draw correctly. The formula of the solution of the second-order linear homogeneous equation with variable coefficients. If a, x, and b, x, are differentiable, the formula of the solution using any C1 and C2 is as follows. From the above, we see the basic structure that the product of the hyper-exponential function of first order and the hyper-exponential function of second order is the solution of the second-order linear homogeneous differential equation with variable coefficients. How to generate? The hyper-exponential functions of n order can be generated using repetitive integrals. This generation method is the basic structure of the hyper-exponential functions. It is one definition method, because it is the sum of the infinite series. In practice, you use a computer to generate and calculate the partial sum. I am an information processing engineer and know that the performance and functions of modern computers and operating systems make it easy to develop programs that generate, calculate, and draw graphs of hyper-exponential functions. Uniform convergence in the wider sense. The following is the proof of uniform convergence in the wider sense of the hyper-exponential functions of n order. Similarly, in general, we thus obtain the following results. This proof is based on the Majorant theorem of Weierstrass. Linear independence. The following is the proof that the hyper-exponential functions of n order are linearly independent one another. Hn, x, is the Wronskian of the n-order hyper-exponential functions. Therefore, Hn, x, is constant. The first term of all functions of the diagonal element of the matrix Hn is 1. And the other elements of the determinant Hn do not have constants. Therefore Hn, 0, equals 1. Thus we see that the Wronskian of the hyper-exponential functions of n order is 1. Therefore we obtain the conclusion that the hyper-exponential functions of n order which are generated using f, x, are linearly independent one another. The list of the differential equations that the solutions by using the hyper-exponential functions. Hermite differential equations. Bessel differential equations. Legendre differential equations. A special solution of the second-order linear non-homogeneous differential equation with variable coefficients. The above is a special solution of the second-order linear non-homogeneous differential equation with variable coefficients. Solution to satisfy the wave equation. I use second-order hyper-exponential functions to show the solution that satisfies the wave equation. Harmonic function. From the above. In addition, the above I is imaginary number. And replace the variable t with y. Therefore, the variable v can be rewritten to a complex number. From the above, you found that the hyper-exponential function of second order is a harmonic function. Extending domains and ranges. I extend the domain and range of second-order hyper-exponential functions to complex numbers. The formula of the solution of second-order linear homogeneous equation with complex variable coefficients. If a, x, and b, x, are regular functions, the formula of the solution using any C1 and C2 is as follows. Publications. Thank you very much.